The James Webb Space Telescope launched on Christmas Day 2021, carrying equipment so sensitive it could detect the heat of a bumblebee standing on the moon. That is not a metaphor. That is the actual engineering benchmark scientists used when designing its infrared detectors. Webb traveled 1 million miles from Earth and parked itself at a gravitational sweet spot, where the combined gravity of Earth and our star holds it perfectly still. Then it unfolded a mirror the size of a tennis court, cooled its instruments down to minus 448 degrees Fahrenheit, and began staring at the oldest light in the universe. Scientists had waited 30 years for this. The concept started in the 1990s. The budget ballooned to $10 billion, and the launch was delayed over 20 times. Every person who worked on it knew the stakes. Webb was designed to answer one foundational question. What did the first galaxies look like, and how did they form? That question sounds clean. The answer turned out to be anything but. Here is what scientists expected. The early universe, just a few 100 million years after the Big Bang, should have been a chaotic, violent place. Gas clouds collapsing under gravity, tiny irregular proto-galaxies sparking to life, messy and dim. Star formation happening slowly, piece by piece, over billions of years, until galaxies gradually assembled themselves into the massive, structured systems we see nearby today. Every simulation, every model, every textbook pointed to the same picture. Small comes first, large comes later. Always. Webb pointed at a tiny patch of sky, a region so small that if you held a grain of sand at arm's length, it would cover it completely. And in that grain of sand slice of the universe, it found hundreds of galaxies from the earliest era of cosmic history. That alone would have been enough to celebrate. Then scientists looked at the sizes, and the room went quiet. Some of these galaxies were massive, fully formed, bright, structured, enormous systems sitting in a period of history when, according to every model ever built, they had no right to exist yet. One of the first candidates identified in early Webb data appeared to hold as many stars as the Milky Way, packed into a universe that was only a few 100 million years old. The Milky Way took billions of years to reach its current size. This galaxy appeared to have done it in a fraction of that time. Astronomer Garth Illingworth, one of the scientists involved in early Webb analysis, described the first results with unusual directness. He said they were finding galaxies that looked like they had been fully cooked when the universe had only been running for a few minutes in cosmic terms. The models did not predict this. The simulations did not allow for this. And the data kept coming. Webb was built to find the first light of the universe and illuminate how everything grew from it. Instead, it found evidence that the growth happened on a timeline that breaks the standard explanation. Scientists did not panic immediately. Science is cautious. The first assumption was instrument error, calibration issues, measurement uncertainty. Every researcher who looked at those early results looked for a simpler explanation first. They did not find one. And the deeper Webb looked, the worse the problem became. What you need to understand going forward is this. The galaxies Webb found are real. They have since been confirmed by multiple teams using independent methods. The data is solid. What remains shattered is the theory that was supposed to explain them. Something built those galaxies faster than the universe should have allowed. And the strangest part, that turns out to be only the first problem Webb handed us. Picture a skyscraper appearing in the middle of a field where the concrete was poured yesterday. That is the closest comparison to what Webb showed the scientific community in its first year of operation. Galaxies are the largest structured objects in the universe. Building one from scratch requires an enormous amount of raw material, gravitational collapse happening over vast timescales, generations of stars being born and dying, and seeding the surrounding gas with heavier elements. Astronomers had spent decades building computer models that simulated this process in extraordinary detail. Those models had a firm prediction. In the very early universe, before about 1 billion years had passed since the Big Bang, you should find only small, irregular, dim galaxies. The big ones come later. That was settled science. Webb found the big ones early, shockingly early. One of the most discussed early discoveries came when a team analyzed a set of objects Webb captured in its first deep field images. Several of these objects showed spectral signatures placing them at a distance corresponding to a time when the universe was only about 500 to 700 million years old, and their brightness levels, when converted into stellar mass, suggested they contained hundreds of billions of stars. Hundreds of billions. Already. At that age. To understand why that is alarming, you need to understand how stars are counted in a galaxy. Astronomers do not count individual stars. They measure the total light output and use it to calculate the combined mass of all the stars present. It is a reliable method, tested across thousands of galaxies. When they applied it to these early Webb targets, the numbers came back enormous. The problem, as a team from the University of Melbourne put it in a paper that made waves across the astrophysics community, is that these galaxies appear to have converted almost all of their available gas into stars, with an efficiency that current physics says is impossible. Normal galaxy formation converts maybe 10% of available gas into stars over billions of years. These objects appeared to have converted 80 to 100% in a fraction of the time. That is like a fire burning all of its fuel in seconds instead of hours, and still producing more heat at the end than at the beginning. Scientists immediately looked for alternative explanations. Could the brightness be inflated by active black holes in the galactic centers, pumping out extra light and making the galaxies look more massive than they are? Possible. That explanation would still require those black holes to be implausibly large for their age, which turns out to be its own separate crisis that comes later in this story. Could there be calibration errors in Webb's instruments, making distant objects appear brighter than they are? Teams went back through the data multiple times. The calibration held. Could the redshift measurements be wrong, placing these galaxies at the wrong point in time? Some researchers raised this possibility carefully, and it is worth sitting with, because it represents a genuine scientific debate happening right now. But the redshift data for the most extreme cases has been confirmed spectroscopically, meaning scientists measured the actual light spectrum line by line, and the distances check out. The galaxies are where Webb says they are, and they are as big as the data suggests. What that means for the standard model of cosmic structure formation is something astrophysicists are still working through. Some are proposing modifications to existing theory. A smaller group is proposing that the theory needs to be rebuilt from its foundation. One thing is already clear. The universe in its infancy was building things on a scale and at a speed that nothing in our current understanding explains. And one chapter ahead, the picture gets considerably darker. Every field of science has a rulebook, a set of equations, models, and confirmed observations that tell you what is possible and what is not. For cosmology, that rulebook is called the lambda-cold dark matter model, and for decades it worked beautifully. It explained how the Big Bang's energy eventually cooled into gas, how gravity pulled that gas into clumps, how those clumps collapsed into the first stars, how those stars clustered into galaxies, how galaxies merged and grew over billions of years into the vast cosmic structures we map today. The model matched observations. It passed test after test. Cosmologists trusted it the way engineers trust the laws of thermodynamics. Webb just handed it a failure it cannot easily absorb. To understand the scale of the problem, consider what the model actually predicts for galaxy formation. In the early universe, shortly after the Big Bang, the universe was almost perfectly smooth. The density variations that seeded all future structure were tiny, about 1 part in 100,000. Gravity worked on those tiny variations slowly, pulling matter together over enormous timescales. The simulations that model this process have been run thousands of times on the world's most powerful computers. They consistently show the same progression. Small, dim, irregular structures form first. Over hundreds of millions to billions of years, they merge and grow. Large, bright, structured galaxies are a late development in cosmic history. Webb's observations describe a universe where that progression happened orders of magnitude faster than any simulation allows. A team of astrophysicists published a direct comparison in early 2203. They took the properties of the most extreme galaxies Webb identified in the early universe and ran them against the predictions of the best available simulations. The result was a discrepancy of roughly a factor of 100 in expected stellar mass. The observed galaxies were up to 100 times more massive than the simulations predicted anything should be at that cosmic age. 100 times. That is the difference between a house cat and a lion, applied to the birth of galaxies. The team's lead author described the situation carefully, noting that if even one of these objects is confirmed, it challenges the existing model. Several have been confirmed. Here is where it starts pressing on something foundational. The lambda-cold dark matter model is not just a theory about galaxies. It is a complete description of how the universe evolves from the Big Bang forward. If galaxy formation happened faster than it allows, something in the underlying physics of the model is wrong. And changing one piece of it without breaking everything else it correctly predicted is extraordinarily difficult. Some researchers are exploring whether the properties of dark matter itself might need to be revised. In the standard model, dark matter is cold, meaning it moves slowly. and it clusters in predictable ways that drive galaxy formation at a predictable rate. If dark matter had slightly different properties in the early universe, galaxy formation could have accelerated. The problem is that changing dark matter's behavior to fix the early galaxy problem tends to break the model's predictions for the universe at later times, which we can test directly and which currently match observations well. Other researchers are looking at the role of dark energy in the early universe. Still others are examining whether the first stars produced far more radiation than expected, compressing surrounding gas and accelerating star formation locally. Every proposed fix introduces new complications. That is the signature of a model under genuine stress. The rulebook is bending. The question every cosmologist is quietly asking is whether it will bend back into shape or whether Webb has found the crack that breaks it open entirely. Stay with that thought, because what Webb found about the brightness of these galaxies makes the structural problem look manageable. By comparison, light carries information. Every photon that reaches Webb's mirror contains a record of where it came from, how far it traveled, and what produced it. Scientists use that information the way a forensic investigator uses evidence at a crime scene. Piece by piece, the light tells a story. The story the light from certain early galaxies is telling does not add up. When astronomers measure the brightness of a distant galaxy, they are measuring how much energy that galaxy is pumping into space every second. This is called luminosity, and luminosity has a ceiling, a hard physical limit rooted in the balance between the outward pressure of radiation and the inward pull of gravity. That limit is called the Eddington luminosity. When a galaxy, or more precisely the stars and black holes inside it, produces radiation at or above that limit, the pressure from the light itself blows apart the gas and dust that feeds star formation. The system regulates itself. You cannot pour infinite energy out of a finite amount of matter in a finite amount of time. Webb found objects in the early universe that appear to violate this budget. Several of the most extreme early galaxy candidates Webb identified produce brightness levels that, when you calculate the implied star formation rate, require those galaxies to be converting gas into new stars at a pace that exceeds the Eddington limit for their estimated mass. Essentially, they appear to be shining harder than physics says they should be able to shine. One way to explain this is that the galaxies are more massive than the measurements suggest. If they contain far more matter than estimated, then the Eddington limit scales up accordingly, and the brightness becomes physically permissible. The problem with that explanation is that it makes the already troubling mass problem even worse. A second explanation, which several teams have explored seriously, is that the initial mass function of stars in the early universe was different from today. The initial mass function is simply the distribution of star sizes that form when a gas cloud collapses. Today, most stars that form are relatively small. If in the early universe almost all stars that formed were enormous, far more massive than typical stars today, a galaxy could produce far more light per unit of gas consumed. This theory is called a top-heavy initial mass function, and it is gaining traction. The catch is that enormous stars live fast and die violently in supernova explosions, seeding the surrounding space with heavy elements. If the early universe was dominated by these massive stars, the chemical fingerprint left behind should be visible in the light of later generation stars that formed from that enriched gas. Webb is actively searching for that fingerprint right now, and preliminary findings are pointing in directions that demand a closer look. A third explanation sits at the more radical end of the spectrum. Some physicists have proposed that the physical constants governing how efficiently matter converts into energy during nuclear fusion were slightly different in the very early universe. If the conversion was more efficient, stars would burn brighter per unit of mass consumed, and the brightness ceiling would be effectively higher. This remains theoretical, but Webb's observations are being used as one of the datasets to test it. The brightness problem is tied directly to the mass problem, which is tied to the formation timeline problem. Pull on any thread, and the others pull back. What is becoming clear to researchers across multiple teams is that these anomalies are connected. They are symptoms of a single deeper inconsistency between the universe Webb is revealing and the universe our models predicted. And connected anomalies are far more dangerous to a scientific model than isolated ones. Something strange was happening in the early universe, something that produced structures larger, brighter, and faster than anything we planned for. Scientists are not alarmed because of one data point. They are alarmed because the data points keep agreeing with each other. What comes next makes the brightness numbers feel almost comfortable by comparison. When a scientific model hits unexpected data, the first move is always the same. Find the simplest explanation that preserves the model. Adjust a parameter, add a correction, keep the core intact. The teams working on Webb's early galaxy problem tried this, methodically, patiently, with every tool available. Every single fix they attempted made something else break. The first proposed solution was systematic measurement error. Perhaps Webb's instruments were somehow inflating the apparent brightness of distant objects, making galaxies look more massive than they actually are. This was the most comfortable explanation because it required no changes to physics, just a hardware correction. Teams spent months going back through calibration data, cross-checking Webb's readings against theoretical predictions and against the few independent measurements that existed for overlapping objects. The instruments held up. The calibration was solid. For the most extreme early galaxy candidates, the brightness could not be explained away as instrument bias. The second proposed fix was contamination from active galactic nuclei. An active galactic nucleus is essentially a supermassive black hole in the center of a galaxy that is actively feeding. And when it feeds, it releases enormous amounts of radiation, far more than the surrounding stars. If the extreme brightness of Webb's early galaxies came from a feeding black hole rather than from star formation, the stellar mass estimate would be artificially inflated. The galaxy would look more massive than it is. This sounded promising. Teams looked for the spectral signatures of active galactic nuclei in the most extreme objects. Some showed hints of activity, but many of the problematic galaxies showed stellar light signatures, meaning the brightness was genuinely coming from stars, not from a central black hole. Removing the active nucleus explanation for those cases left the mass problem fully intact, and here is where the fix created its own problem. In the cases where active galactic nuclei did seem to be contributing, the black holes required to produce that luminosity would themselves be implausibly large for their cosmic age. So the proposed fix did not dissolve the anomaly. It transferred it to a different and equally unexplained place. The third attempted fix was a revision to the assumed dust content of early galaxies. When astronomers estimate stellar mass from brightness, they apply corrections for dust, which absorbs and scatters light, making galaxies appear dimmer than they are. If early galaxies had less dust than assumed, the raw brightness would correspond to less stellar mass. Recalibrating the dust correction could bring the mass estimates down. This approach helped slightly for some objects. For the most extreme cases, even setting the dust correction to 0, assuming completely transparent galaxies with no dust at all, did not bring the mass estimates into a range the standard model could accommodate. The fourth proposed fix was the most conceptually ambitious. Some researchers suggested that the galaxies identified as extreme outliers were not actually representative, that Webb had stumbled onto a statistical fluke, a cluster of unusually massive objects in an unusually dense patch of early universe that happened to fall in its field of view. Then other teams pointed Webb at different patches of sky. They found the same thing. The massive early galaxies are distributed broadly across different regions of the observable universe. The statistical fluke explanation collapsed. By the end of Webb's first year of deep field observations, the scientific community had reached an uncomfortable consensus. The anomalies are real. The fixes do not fix them. And the deeper you look into the data, the more the standard model strains against what is actually there. What that means for the age of the universe itself is the question that started keeping cosmologists up at night. That number has been printed in textbooks, cited in thousands of papers, and treated as one of the most precisely measured quantities in all of science. It is the age of the universe, derived from the rate at which the universe is expanding, and from the temperature and pattern of the oldest light we can detect, called the cosmic microwave background. Webb's early galaxy discoveries are putting pressure on that number in a way that is difficult to ignore. Here is the logic, laid out plainly. To build a galaxy containing hundreds of billions of stars, you need time. You need gas clouds to collapse into stars. You need those first stars to live and die and enrich the surrounding gas with heavier elements. You need subsequent generations of star formation to build up the stellar population. You need gravity to organize all of it into the structured rotating disk shapes Webb is observing in some of these early objects. When astronomers simulate this process, even under the most optimistic assumptions about star formation efficiency, it takes several hundreds of millions of years at an absolute minimum to produce a galaxy of the mass Webb is finding, probably longer. Now place those galaxies at the distances Webb is measuring. Some of them sit at a point in cosmic history when the universe was only 400 to 600 million years old. That means, working backward, the gas that formed them had to start collapsing into stars almost immediately after the Big Bang, before the universe had time to cool properly, before the structural scaffolding provided by dark matter could realistically have formed. A team of cosmologists published a direct analysis of this in 2003. framing the problem in terms of what they called a timeline budget. They asked a simple question. Given the age of the universe at the redshift where these galaxies sit, is there enough time for standard galaxy formation physics to produce what Webb observed? The answer for the most massive objects was no. The budget ran out. Supporters of the standard model argue that the formation timeline can be compressed if certain conditions in the early universe were more extreme than assumed. Higher density fluctuations in the initial conditions of the Big Bang could seed faster gravitational collapse. Modified dark matter behavior could accelerate the process. These are legitimate areas of active research. But a growing minority of cosmologists is asking a more fundamental question. What if the universe is simply older than 13.8 billion years? If the universe had several more billions of years of history before the formation of the cosmic microwave background signal we use to date it, or if the expansion history of the universe is more complex than the standard model assumes, then the timeline budget opens up. The massive early galaxies stop being anomalies and become expected features of a longer cosmic history. This idea connects to deeper disputes in cosmology about how accurately we are measuring cosmic expansion. Disputes that were already simmering before Webb launched, and that the telescope's data has now intensified considerably. The standard timeline is not collapsing overnight. Changing the age of the universe requires reworking multiple interlocking measurements that currently agree with each other. That is hard to do cleanly, but the cracks are visible, and the next piece of data Webb delivered tore one of those cracks considerably wider. Dark matter is the universe's most important invisible ingredient. You cannot see it. No telescope, including Webb, detects it directly. It emits no light, reflects no light, and absorbs no light. The only reason scientists know it exists is because of what it does to everything around it. It bends light through gravitational lensing. It holds galaxy clusters together that would otherwise fly apart. It creates the cosmic scaffolding along which visible matter, gas, and stars and galaxies arranges itself. For 4 decades, the standard model has treated dark matter as cold and slow-moving, interacting with ordinary matter only through gravity, clumping in predictable halos around galaxies, driving structure formation in a way that computer simulations could reproduce with remarkable accuracy. Webb has introduced a complication. The standard cold dark matter model predicts a specific structure for how galaxies and their surrounding dark matter halos should look in the early universe. Small dark matter clumps form first, merge over time into larger ones, and the visible galaxies embedded in those clumps follow the same pattern. Slow, hierarchical, predictable. What Webb showed is galaxies in the early universe that are too structured, too large, and too organized to sit comfortably inside dark matter halos of the size standard theory predicts should exist at that cosmic age. Several independent research groups ran comparisons between Webb's early galaxy observations and the best available cold dark matter simulations. The simulations consistently underproduced massive structured galaxies in the early universe by a significant margin. Something in the dark matter behavior was allowing visible matter to organize faster than the simulations allowed. One proposal gaining serious attention is that dark matter in the early universe may have behaved less like a slow cold fluid and more like a quantum wave spread across large distances. This idea, called fuzzy dark matter or ultralight dark matter, predicts that on small scales, dark matter forms smooth cores rather than the dense spiky clumps that cold dark matter theory predicts. The difference in structure changes how gas collapses and how quickly early galaxies can form. The mathematics of fuzzy dark matter allows for faster early galaxy assembly in certain mass ranges, which aligns better with Webb's observations. But it creates new tensions in other parts of the model, particularly in predictions for the number of small satellite galaxies orbiting larger ones, a count that observations currently match reasonably well under cold dark matter theory. A second, less mainstream proposal is that dark matter can interact with ordinary matter slightly more than currently assumed, through a weak force that is not gravity, but is detectable in the statistics of early structure formation. If dark matter had even a tiny additional interaction in the early universe, the timeline for galaxy assembly could have accelerated enough to explain part of what Webb sees. Webb is providing the most precise measurements of galaxy morphology and mass in the early universe that astronomers have ever had. Every new deep field image adds data points that constrain what dark matter can and cannot be doing. The unsettling conclusion so far is that the dark matter model that made decades of cosmological predictions work may need a significant revision. The version of dark matter that fits Webb's early universe does not look exactly like the version that fits the nearby universe. That tension is the kind that usually precedes a major shift in understanding. And the structural surprises Webb found inside those early galaxies make the dark matter problem feel like only the surface layer of something far deeper. Chaos was supposed to define the early universe. When scientists modeled what the first galaxies would look like up close, the image they arrived at was turbulent. Violent, gas crashing in from all directions, collisions between proto-galactic clumps happening constantly, stellar populations wildly mixed in age and composition. The early universe was a construction site mid-explosion, and the galaxies forming inside it should have looked the part. Webb pointed its mirror at galaxies from within the first billion years of cosmic history, and found something that genuinely surprised the research teams analyzing the images. Some of these ancient galaxies looked calm, structured, disk-like, rotating. A disk galaxy is exactly what it sounds like, a flat, organized structure where stars and gas rotate together around a central point. Like a slow spinning platter, the Milky Way is a disk galaxy. So is our neighbor Andromeda. Disk galaxies require stability to form. The rotating structure only develops when a galaxy has had enough time to settle, when the violent inflows and mergers that characterize early growth have calmed down enough for rotation to dominate. According to the Standard Model, disk galaxies should be a later development in cosmic history. Early galaxies should be irregular, clumpy, chaotic. In 2003, a team analyzing Webb imaging published results showing that a significant fraction of galaxies, from the first few billion years of the universe, already had well-defined disk structures. In some cases, the disks were present in galaxies observed less than 700 million years after the Big Bang. The fraction of disk galaxies at that early epoch was far higher than simulations predicted. In the simulations, galaxy mergers and the constant bombardment of infalling material should disrupt disk formation repeatedly during that era. The simulations predicted irregular, disturbed morphologies dominating the early galaxy population. Webb saw order where chaos was expected. One proposed explanation is that the gas in early galaxies was fed in along specific channels, cold streams of gas flowing along filaments of dark matter, in a way that naturally produces rotation rather than disrupting it. This idea, called cold stream accretion, has been theorized for years. Webb's observations are now providing the first direct visual evidence that something like it was operating at cosmic scales. A second explanation is tied back to the dark matter problem. If dark matter in the early universe formed smoother, more uniform halos rather than the clumpy, merger-prone structures cold dark matter predicts, the environment inside those halos would be calmer, and disk formation could proceed more efficiently. What makes these disk detections particularly striking is their implication for star formation history. Disk structures are efficient at turning gas into stars in an organized, sustained way. A rotating disk galaxy sustains star formation across its entire extent simultaneously, while a chaotic, irregular galaxy forms stars in bursts and gaps. If early galaxies were disk-dominated, they could have sustained high rates of star formation for longer periods, which would help explain the mass problem from earlier. The pieces are beginning to connect in a picture nobody built in advance. A calmer, more structured early universe than anyone predicted. Dark matter behaving differently than assumed. Galaxy formation running on a faster and more organized schedule than any simulation produced. And somewhere inside the most extreme of those early galaxies, something else was already fully assembled and waiting. Something that should have taken billions of years to build. Something that entire galaxies are built around. Finding a single massive galaxy in the early universe is alarming enough. Finding a group of them, gravitationally bound to each other, pulling together into a structured cluster, is a different category of problem entirely. A galaxy cluster is a collection of galaxies held together by mutual gravity, often containing hundreds or thousands of individual galaxies, enormous amounts of hot gas between them, and vast halos of dark matter binding it all. Galaxy clusters are the largest gravitationally bound structures in the observable universe. Building one takes time, enormous amounts of time. Galaxies have to form first, then drift close enough to feel each other's gravity, then gradually fall into a shared gravitational well over billions of years. The Standard Model predicts that genuinely massive bound galaxy clusters should appear only after several billion years of cosmic evolution. Webb found candidates for bound galaxy structures, sometimes called protoclusters, at redshifts corresponding to the universe being less than 1 billion years old. One particularly striking discovery involved a structure observed in 2003, containing multiple massive galaxies concentrated in a region of space far smaller than you would expect by chance. The galaxies showed consistent redshifts, meaning they were at the same distance, and their spatial distribution was consistent with gravitational association. They were moving together, pulling toward a common center in the early universe. If confirmed as a genuine gravitationally bound system, this structure would represent one of the earliest known protoclusters ever detected, sitting in a cosmic epoch when the standard model says such structures should only be beginning to form their very first individual galaxies, not organizing into clusters. Run that sentence again slowly. When this cluster appears to exist, the standard model predicts the universe should still be working on building the individual galaxies that would eventually become cluster members. The individual components and the collective structure both arrived too soon. Teams looking at this and similar structures have raised specific technical concerns worth acknowledging. Confirming a true gravitational bound system at that redshift requires spectroscopic confirmation of multiple galaxy redshifts to rule out projection effects, where galaxies at slightly different distances appear clustered on the sky by chance. Some of these structures have been spectroscopically confirmed. Others are still awaiting full confirmation. This remains an active area of research, and caution is appropriate. But even the confirmed cases represent a challenge, and the theoretical response has been revealing. When cosmologists tried to reproduce these early protoclusters in updated simulations, they found they could do it only by significantly boosting the initial density fluctuations in the early universe, far beyond the values measured in the cosmic microwave background. In other words, to make the simulations match what Webb sees, you have to change the starting conditions of the universe. Changing the starting conditions is a significant move. The pattern of density fluctuations in the early universe is one of the most precisely measured quantities in cosmology, derived from decades of observations of the cosmic microwave background. Altering it to fix the protocluster problem could break the agreement between the standard model and those background measurements. The early universe, according to Webb, was building bigger structures earlier than any model allowed, and the mechanism that was supposed to control the pace of structure growth, the distribution of matter at the very start, may have been operating differently than scientists measured, which raises a question that some researchers are now openly asking. How certain are we that we are measuring those early conditions correctly? And how certain are we about how to interpret the signal that carries that information? The answer to those questions takes us somewhere deeply uncomfortable. Redshift is the ruler cosmologists use to measure the universe. When a galaxy moves away from us, its light gets stretched. The faster the recession, the more the light stretches toward longer, redder wavelengths. By measuring how much the light has stretched, astronomers calculate how far away a galaxy is. And, because the universe has a known expansion history, how long ago that light was emitted. Redshift is the tool that turns light into a timeline. It is a reliable tool, tested across millions of galaxies, cross-validated against independent methods like the distance ladder, standard candles, and gravitational lensing. Cosmologists trust redshift measurements the way engineers trust a calibrated ruler. A small but growing group of researchers is now asking whether that ruler has systematic uncertainties at the extreme distances Webb is probing, uncertainties that could quietly skew the ages assigned to the most distant galaxies. This is worth taking seriously because the claim is specific and technical rather than vague. Here is the concern. For nearby galaxies, redshift can be confirmed using the spectra of individual well-known atomic emission lines, specific wavelengths of light that atoms emit when heated. When those lines show up shifted toward the red end of the spectrum, the shift directly gives you the recession velocity and therefore the distance. For the most distant galaxies Webb is finding, spectroscopic confirmation is available for some but not all objects. A subset of the most extreme early galaxy candidates were initially identified using photometric redshift estimates, which means astronomers measured the total brightness of the galaxy through multiple color filters and used statistical models to estimate the redshift rather than detecting specific spectral lines directly. Photometric redshifts are less precise than spectroscopic ones. They carry error bars, and at extreme distances, a photometric redshift error can shift a galaxy's estimated age by hundreds of millions of years. A team of researchers pointed out in a 2022 paper that several of the galaxies generating the most alarm from Webb's first data releases had photometric redshifts rather than spectroscopic ones. They argued that before declaring a crisis in cosmology, every extreme outlier needed to be confirmed spectroscopically. Since then, follow-up spectroscopic campaigns using Webb itself have confirmed the extreme redshifts of several of the most prominent objects. The most massive and most discussed early galaxy candidates now have spectroscopic confirmation. The measurement crisis argument has weakened considerably. For the strongest cases, however, the broader methodological point stands. Cosmology at the frontier of what Webb can observe is operating in a regime where measurements are hard, confirmations take years, and the error bars are large enough to matter for theoretical interpretations. What this means practically is that the crisis in the standard model is real, but its precise severity is still being calibrated. The core finding, massive galaxies existing earlier than expected, is confirmed. The exact degree to which they exceed model predictions is still being refined. That nuance matters. Good science lives in the nuance. But even the conservative, well-confirmed version of Webb's early galaxy results is enough to demand explanation. And the most provocative explanation, the one gaining traction in a corner of the cosmological community that most researchers are watching with a mix of fascination and skepticism, involves throwing out the age of the universe entirely. 13.8 billion years is not a measurement everyone agrees with. That is a statement that requires immediate qualification. The vast majority of cosmologists accept the standard age. It is derived from multiple independent measurement methods that converge on the same answer. The cosmic microwave background, the expansion rate of the universe, the ages of the oldest stars, the abundance of light elements produced in the Big Bang, they all point to roughly the same number. But convergence is not the same as certainty, and Webb's data has given new oxygen to a minority view that has existed at the fringes of cosmology for years. The universe may be significantly older than the standard model says. The leading proponent of this view in recent years is Rajendra Gupta, a physicist at the University of Ottawa, who published a paper in 2023 arguing that combining two modifications to standard cosmological theory could push the age of the universe to approximately 27 billion years, nearly double the standard estimate. The first modification he invokes is an idea called tired light, originally proposed decades ago, which suggests that light loses energy as it travels across cosmic distances, making distant objects appear more redshifted than their actual recession velocity would warrant. Standard cosmology rejected tired light decades ago because it makes predictions about the appearance of distant supernovae that observations have not supported. Gupta pairs tired light with a second concept involving the slow evolution of fundamental physical constants over cosmic time. If certain constants governing the behavior of matter and energy changed gradually across cosmic history, the calibration tools used to measure the universe's age could carry systematic offsets. Most cosmologists have not embraced this framework. The problems with tired light are well documented, and invoking evolving physical constants is a major move that requires independent evidence beyond galaxy formation anomalies to be compelling. Gupta's paper received substantial criticism from mainstream researchers, who argued the proposed modifications introduced more problems than they solved. The reason this minority view is worth discussing is not that it is probably correct. The reason is that Webb's observations gave it enough observational motivation that serious researchers are spending time engaging with it, rather than dismissing it outright. That is a meaningful shift. More moderate versions of the older universe argument avoid tired light entirely and focus instead on revisions to the expansion history of the universe. If the rate of cosmic expansion varied over time in ways not captured by the standard model, the age estimate derived from the current expansion rate could be an underestimate. Some researchers examining Webb data have proposed that the universe's expansion decelerated more in certain periods and accelerated differently in others, in ways that could add billions of years to its total age without requiring changes to fundamental physics. This connects to a crisis in cosmology that predates Webb, and that the telescope has since amplified into a genuine emergency: the Hubble tension. And the Hubble tension, once you understand what it actually means, changes the entire frame of everything Webb has found. Every galaxy beyond our local group is moving away from us, and the more distant it is, the faster it recedes. The rate of that expansion is called the Hubble constant, named for the astronomer Edwin Hubble, who first measured it in the 1920s. Measuring the Hubble constant precisely is one of the central projects of modern cosmology. The number tells you how fast the universe is growing today, and combined with other measurements, it tells you how old the universe is and what its future will look like. For the past decade, cosmologists have had a problem. Two completely independent methods of measuring the Hubble constant give two different answers that refuse to agree. The first method looks at the early universe. Scientists analyze the cosmic microwave background, the ancient light released when the universe was only 380,000 years old, and use it to calculate how fast the universe should be expanding today, given its initial conditions. This method gives a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method looks at the nearby universe. Scientists use a chain of distance measurements built on Cepheid variable stars, a type of star whose brightness pulses in a predictable rhythm that reveals its true luminosity, combined with observations of a specific type of stellar explosion, called a Type 1a supernova, to measure how fast nearby galaxies are actually receding today. This method gives approximately 73 kilometers per second per megaparsec, 67 versus 73. That gap sounds small. In cosmology, it represents a catastrophic inconsistency. The early universe and late universe measurements of the same fundamental constant of nature do not agree. This discrepancy was already a serious problem before Webb launched. Some researchers hoped Webb would resolve it by providing better distance measurements and either validating one method or identifying the systematic error responsible for the gap. Webb did the opposite. It made things worse. A team led by astronomer Adam Rees used Webb to obtain precision measurements of Cepheid variable stars in nearby galaxies, dramatically reducing the sources of error that had previously been suspected as the cause of the tension. The results, published in 2023, showed that the late universe measurement of the Hubble constant remained stubbornly above 69, well above the early universe value. The measurement error had shrunk. The tension had not. If anything, the improved precision meant the discrepancy was now harder to explain away as a measurement artifact. Webb essentially ruled out the most comfortable escape route. What remains as possible explanations falls into two uncomfortable categories. Either one of the measurement chains contains a systematic error that no one has yet identified, despite years of intense scrutiny by competing teams, or the standard cosmological model is missing something fundamental about how the universe expanded across its history. The second possibility, if true, would require a revision to our understanding of dark energy, the force driving cosmic expansion, or to the nature of the early universe's content. Either option is a major structural change to the model. The Hubble tension and the early galaxy problem are separate crises, but they share a common implication. The standard model of cosmology is being measured with increasing precision from two different directions simultaneously, and it is not passing both tests. Something about the universe, its age, its expansion history, its content, or its initial conditions, is different from what the standard model describes. And Webb, the most precise instrument humanity has ever aimed at the sky, is the one delivering the evidence. The next question is how Webb actually sees all of this. And the answer to that question is as strange as anything the telescope has found. Every previous generation of astronomers looked at the universe through visible light, then ultraviolet, then X-ray and radio waves. Each new wavelength revealed a layer of the universe that had been invisible before. Webb operates primarily in infrared light. That single choice changed everything. Infrared is heat radiation. Objects that are too cool to glow in visible light still glow in infrared. Clouds of gas and dust that absorb and block visible light are largely transparent to infrared, and light from the very early universe, originally emitted as ultraviolet or visible light by the first stars and galaxies, has been stretched by cosmic expansion over billions of years until it arrives at Earth as infrared radiation. To see the early universe in its own light, you need an infrared telescope. And to see faint infrared signals from 13 billion light years away, you need that telescope to be cold, very cold, so that its own warmth does not overwhelm the signal. Webb achieves this through a 5-layer sunshield the size of a tennis court that keeps its instruments in permanent shadow. At its operating temperature of -448 degrees Fahrenheit, Webb emits almost no infrared radiation of its own. Its detectors are essentially dark, waiting to receive. The result is a resolution and sensitivity combination that no previous instrument achieved. Webb can detect a candle on the moon. It can measure the heat signature of a planet orbiting a star 40 light-years away, and it can capture the infrared light of galaxies that formed when the universe was less than 500 million years old. But resolution alone does not explain what Webb has revealed. The deeper advantage is spectroscopy. Webb can take the light from a distant galaxy and split it into its component wavelengths with enough precision to identify specific chemical elements by their unique spectral fingerprints. Carbon, oxygen, hydrogen, even complex molecules. This is where Webb stopped being merely a bigger telescope and became a fundamentally different tool. Previous telescopes could identify distant galaxies and estimate their distances. Webb can tell you what those galaxies are made of, what chemistry was happening inside them, what stage of evolution they had reached. It can detect the presence of molecules in the atmospheres of planets orbiting other stars, at distances that were completely out of reach for any prior instrument. The infrared capacity also cuts through something that blocked previous telescopes from seeing into the centers of star-forming regions: dust. Stellar nurseries, the dense gas clouds where new stars are born, are surrounded by thick shells of dust that scatter visible light, the way fog scatters headlights. To infrared light, that dust is nearly transparent. Webb sees directly into the hearts of regions where stars are being born right now, and by extension, into the conditions that produce the first stars in history. Those first stars, called population 3 stars by astronomers, have never been directly detected. Webb is the first instrument capable of potentially seeing them, and the search for their signatures is ongoing. What Webb has already found, near the expected epoch of their formation, has raised questions that no one had prepared a ready answer for. What is already producing direct images of structure inside stellar deaths, inside the cores of galaxies and inside the chemical evolution of the early universe, is revealing a cosmos more layered and more chemically complex than the standard model described. And the most surprising chemical discovery Webb has made, found in a place where it had absolutely no right to exist, is coming up next. Every atom of carbon in your body was forged inside a star that died before our star was born. That is confirmed science. The first generation of stars, the population 3 stars, formed from almost pure hydrogen and helium, the only elements produced in the Big Bang. These stars had no planets, no chemistry rich enough for life. They were enormous by the standards of stars today, potentially hundreds of times more massive than our star, burning so hot and so fast that they lived for only a few million years before exploding. When they exploded, they seeded the surrounding gas with the first heavy elements: carbon, oxygen, iron, and everything beyond. Every subsequent generation of stars, and every planet formed from stellar debris, carries those first-generation elements in its composition. Finding population 3 stars directly would be the closest thing to witnessing the universe's first creative act. It would confirm theories about the very first moments of structure formation, and provide a direct window into the chemistry that made everything else possible. Webb has never directly imaged a population 3 star. They formed and died so long ago that only their influence remains. But Webb is operating at wavelengths and sensitivities that theorists believe should be sufficient to detect them under the right conditions. In 2203, a team reported intriguing spectroscopic signals from an extremely distant galaxy cluster, acting as a gravitational lens that was magnifying light from galaxies behind it. Inside the magnified light, they found spectral signatures that were unusually free of heavy elements, suggesting a stellar population with extremely low metallicity. Low metallicity is the chemical signature of stars that formed before heavy elements were widely distributed, which is the expected property of population 3 star-forming regions. This was not a confirmed detection of individual population 3 stars. The team was careful about that distinction. The signal was consistent with a population 3 contribution, meaning the chemistry of what they observed could include population 3 stars, but could not rule out other explanations. More data is needed, and follow-up observations are planned. The reason this matters beyond the immediate discovery is what the signals suggest about the timeline of chemical evolution. If population 3 star-forming regions were still active at the cosmic age implied by the redshift of these objects, it means the transition from the primordial chemistry of the early universe to the heavier element-rich chemistry needed for rocky planets, and eventually life may have taken longer in some regions than standard models predict. Some corners of the early universe may have remained chemically primitive far longer than average, with pockets of near-pristine hydrogen and helium gas persisting, while other regions were already being enriched by exploding first-generation stars. This uneven chemical evolution of the early universe is a prediction that some models make and others do not. Webb's findings are beginning to favor the models that predict patchiness, suggesting the universe's first chemical steps were messy and uneven rather than smooth and uniform. And in the same epoch, Webb is probing for the first stars. It found something else, something that should not have been fully assembled that early in cosmic history. Something so massive it bends light around itself. Something that changes the story of everything that comes after. At the center of nearly every large galaxy in the observable universe sits a supermassive black hole. Our own galaxy has one, called Sagittarius A star, with a mass equivalent to 4 million stars like our own. Supermassive black holes are not rare objects. They are standard furniture in the galactic universe. But their existence raises one of the deepest unsolved problems in astrophysics. How did they get so big? A stellar mass black hole forms when a massive star collapses at the end of its life. These objects typically carry a mass of a few tens of times that of our star. For a black hole to grow from stellar mass to supermassive, it has to consume material. Gas, dust, other stars, smaller black holes. It has to feed. and feeding takes time. The maximum rate at which a black hole can feed is set by the same Eddington limit discussed earlier in the context of galaxy brightness. Feed too fast, and the radiation pressure from the infalling matter blows away the surrounding gas, cutting off the supply. A black hole, accreting at the maximum rate allowed by physics, would take a very long time to grow from stellar seed to supermassive scale. Estimates, working backward from realistic seed masses and applying the Eddington limit continuously, suggest it should take at least 1 billion years of essentially uninterrupted maximum accretion to grow a black hole to even a few 100 million solar masses. Webb found black holes in the early universe that appear to be billions of solar masses in size, already mature, sitting in galaxies that existed when the universe was less than 1 billion years old. One of the most discussed cases involves a quasar, an extremely active black hole, detected at a redshift placing it at a cosmic age of roughly 700 million years. The black hole powering it appears to carry a mass of approximately 1.6 billion solar masses. At that cosmic age, by standard calculations, there has simply not been enough time for a black hole to grow that large from any known starting point. Teams working on this problem have proposed several mechanisms that could allow faster growth. One involves the direct collapse of massive gas clouds in the early universe into black holes without passing through a stellar phase. These direct collapse black holes could potentially start with masses of 100,000 solar masses or more, giving them a significant head start. The problem is that the conditions required for direct collapse are very specific, and producing enough of them to explain the observed population of early supermassive black holes stretches the available initial conditions considerably. Another proposal involves the merger of many smaller black holes in dense early star clusters, building up mass faster than individual accretion allows. This mechanism works in principle, but requires unusually dense stellar environments that are themselves difficult to explain, without running into the galaxy formation problems described earlier. A third and more radical proposal involves super-Eddington accretion, where black holes feed faster than the standard limit by briefly overcoming the radiation pressure through geometry, feeding along a narrow disk while blowing gas away in perpendicular jets. There is some observational evidence that this occurs in nearby galaxies under specific conditions, but whether it can operate continuously for long enough to build the most extreme early black holes is debated. Every proposed solution is possible in principle. None is confirmed, and the black holes keep appearing, earlier and larger than any single mechanism cleanly explains. Something was building these objects at a pace that breaks every theory of how they grow, and what that means for the galaxies built around them changes the entire story of how the visible universe assembled itself. The standard picture of galaxy evolution places supermassive black holes as passengers. The galaxy forms first from collapsing gas clouds. Stars ignite. Structure develops. Eventually, as the galaxy matures, a central black hole grows at its core, fed by gas channeled inward over time. Galaxy first, black hole second. That was the accepted sequence. Webb shattered it. In the first billion years of the universe, Webb found evidence of supermassive black holes existing in galaxies where the stellar mass of the galaxy itself was small relative to the black hole's mass. In nearby present-day galaxies, there is a well-established relationship. The mass of the central black hole is roughly 1/10 of 1% of the total stellar mass of the surrounding galaxy. This ratio holds across thousands of galaxies in the local universe, with remarkable consistency. In several of Webb's early universe detections, the central black hole accounts for a much larger fraction of the total mass of its host galaxy. In some extreme cases, the black hole appears to be comparable in mass to the stars surrounding it, instead of being the tiny central seed the standard picture describes. A black hole is massive as its host galaxy, in an infant universe. Astronomers call this a heavy seed problem, and it is directly connected to the galaxy formation puzzle. If the standard formation sequence is galaxy first, black hole second, then finding black holes that are proportionally enormous compared to their host galaxies in the early universe implies either that the black hole formed first and the galaxy was built around it, or that the black hole grew much faster than its galaxy in the early universe, which requires specific mechanisms that current theory cannot easily provide. The first option, black hole first, is genuinely radical. It would mean that in the early universe, the central black hole was not a product of galaxy evolution, but a driver of it. The gravitational influence and the radiation field of the growing black hole could have shaped the distribution of gas around it, controlling where and how fast stars formed in the proto-galactic cloud. There is a concept in galaxy evolution called black hole feedback. In nearby galaxies, The jets and radiation from an active central black hole can regulate star formation by heating and expelling gas from the galaxy, eventually shutting down star formation entirely. If this feedback operated in reverse in the earliest galaxies, with the black hole's gravity initially concentrating gas and triggering star formation rather than suppressing it, it could explain some of the observed mass ratios. This idea requires a fundamentally different understanding of the relationship between black holes and their host galaxies in the early universe, with implications that cascade through every model of how galaxies evolve from birth to maturity. The confirmation of even a few well-characterized examples of this extreme mass ratio in Webb's deep field data would require updating the models that describe galaxy-black hole coevolution. Those models currently underpin most of our understanding of why galaxies look the way they do today, including our own. Something else was happening in the early universe, a different sequence, a different dynamic, and to understand what that might be, you need to see the structure the early universe was using as its building grid. Something vast and woven, and if you look at it long enough, almost uncomfortably familiar. Zoom out far enough from any galaxy, any cluster, any supercluster, and the universe reveals a structure so large that calling it a structure feels inadequate. Galaxies do not scatter randomly through space. They collect along thin filaments of dark matter and gas that stretch across hundreds of millions of light years, forming the boundaries of enormous empty regions called voids. Where filaments intersect, clusters of galaxies pile up. Where they connect to other filaments, superclusters form. The whole arrangement resembles a three-dimensional spider web of almost incomprehensible scale. Cosmologists call this the cosmic web. It is the largest known structure in the universe. Webb has now imaged sections of the cosmic web in more detail than any previous telescope, capturing the filaments as genuine visible structures rather than statistical inferences from galaxy surveys. In several deep field images, the alignment of galaxies along specific axes, tracing the invisible dark matter threads beneath them, is visible directly in Webb's data. And here is the part that stops people cold when they first encounter it. A team of researchers compared the structure of the cosmic web, as mapped by galaxy surveys, with the structure of a human brain's neural network, as mapped by electron microscopy. The comparison was partly an exercise in mathematical structure analysis, not a metaphysical claim. They measured things like the fraction of matter contained in nodes versus filaments, the connectivity of the network, the clustering behavior at different scales. The quantitative similarity between the two networks was striking enough to merit publication.